Hello and welcome to today's tutorial. So today we are going to talk on the linear systems. So here the input and output, we are trying to represent this in terms of the random process, and we are trying to relate this with the autocorrelation function and then with the spectral densities. So let us switch back to the screen and we'll see the linear systems analysis. So now we'll talk about the linear system. So what is a linear system? So for example, let us take uh, a system here, which is an LTI system. LTI system means a system where it is linear as well as a time invariant, means it doesn't vary. If the input shifts with certain time, output also shifts with a certain time. It means it is invariant of time change. It is invariant of time. So now, for example, if we consider say any arbitrary signal as x of t, then we will get the output y of t. So to find the system behavior, so first we should know what is the impulse response. To find the impulse response, so we will give this in terms of an impulse, and whatever the output we will get, we will call that as impulse response. So then that is called as h of t. So then we model this system as the impulse response h of t. So now after that we can apply any arbitrary signal to this system as x of t, and then we'll obtain the y of t, and then this y of t is nothing but it is the convolution of x of t with the impulse response h of t. So that will be the output. Now since this is, we are talking about the continuous time random process here, then we are going to relate this with the Laplace transform, because the extension of the Fourier transform for a continuous time arbitrary signal is the Laplace transform. So then if you want to write this and apply the Laplace transform of this case, so y of t will become y of s, h of t will become h of s, and x of t will become x of s. And with the convolution property, if we apply the Laplace transform, so this will become a multiplication in the Laplace domain. So then this will become y of s is equal to, that is h of s into x of s. So here h of s is called as a transfer function in terms of the Laplace domain. So first we will take the normal case in terms of the normal x and y, then we are going to relate this to our random process. So now if you want to write this in terms of y of t, so then y of t is equal to an integral of say 0 to infinity, it is h of u into x of t minus u into du. So this is the convolution integral equation, but rather than the summation limits ranging from minus infinity to plus infinity, we have considered the limits from 0 to infinity, because we will consider that the impulse response h of t is equal to 0 for the value of t less than 0. That is why all its impulse responses are 0, because if we take practically any system or any signal, it starts at the definite time and ends at the definite time. It has some starting instant and the ending instant. So the starting instant itself we call it as 0, and it ends at some point. So then if we try to relate this this normal x of t signal to our random process case, so then this can be defined as, in terms of y of t is equal to an integral of 0 to infinity, that is h of u into, now this can be written in terms of the capital X to represent this random process, it's not any arbitrary signal. So now it is x of t minus u into du. Now let us find the mean of this y of t process here. So y of t process here, it is now the random process we are talking about. Let me save this page. Let us find the mean of y of t. So that is defined by mu y is equal to an expectation of y of t is equal to an integral of 0 to infinity, it is h of u into expectation of x of t minus u into du. So remember one thing, here expectation is only applicable for the random process, it is not applicable for anything, any other sequence or any other signal. Here h of tau is the impulse response, so that has become a constant in this case because it is not a random process. So that is why an expectation cannot be applied on such kind of thing, so it will be treated as a constant. So expectation is only applied on the random process, in this case it is x. And the impulse response is constant and its expectation is not a constant. So we know that the expectation of x is nothing but mu x. So let me rewrite this equation. So this is integral 0 to infinity. So this will be h of u into mu x into dx. So now the integral is with respect to only the u term and the mean is the constant. So I'll take this mean outside. So it is mu x into integral of 0 to infinity. It is h of u into du. So this is our mean of this linear system. Okay. So now if you want to relate this with the Laplace transform, so how do we relate with the Laplace transform? So what is the Laplace transform equation basically? So that is nothing but, say let us define, so h of s is equal to an integral of h of s equals 0 to infinity into h of t into e power minus st into dt. So now if you want to relate this equation with this equation, how do I do it? So I can consider this by considering the value of s is equal to 0. So if I substitute s equal to 0 in this case, so then it will be h of s equal to 0 integral of 0 to infinity, integral 0 to infinity, this will be h of t. Now it is e power 0, so e power 0 is 1, so this will become, it is just dt. So now this equation can be applicable to this equation. Then finally we can conclude this as, if I move this term side, so then I can write this as, that is mu y is equal to mu x into h of 0. So here h represents the transfer function. So therefore x of t is a zero mean random process and y of t is also a zero mean random process. Now let us look into the cross correlation of this y of t and x of t. Let's save this page. Let us look into the cross correlation of y of t and its x of t in case of linear system. So now from the previous definition, we know that mu y is equal to integral of 0 to infinity, that is h of u into an expectation of x of t minus u into du. Then if we take the cross correlation function, so that is defined as rxy of tau is equal to, it is an expectation of x of t with x of t plus tau. If we apply this in this equation, then we can write this as integral 0 to infinity h of u into an expectation of x of t, an expectation of x of t into x of t plus tau minus u into du. So this integral is nothing but the convolution function. So this I can write this as Rxy of tau is equal to an integral of 0 to infinity. It is h of u into, this is nothing but it is Rx of tau minus u into du. So this is the this is the cross correlation function in terms of the linear equation, or in terms of the linear system. So this is the equation. Now we will relate this with the spectral density, cross spectral density. So we know the cross spectral density from the previous derivation, that can be written as Sxy of omega is equal to an integral of minus infinity to plus infinity. This is Rxy of tau into e power minus j omega tau into d tau. So now we are going to substitute this term here in this equation, so that we'll see in the next page here. So when we substitute, we'll get Sxy of omega is equal to an integral from minus infinity to plus infinity, an integral from 0 to infinity here, then h of u into Rx of tau minus u into du into e power minus j omega tau into d tau. So once we're here in this equation as 0 to infinity, we'll take this term outside, h of u term, then integral of minus infinity to plus infinity, that is Rx of tau minus u into e power minus j omega tau into d tau. So here one more term is missing, so this is du into d tau is there. Now d tau into du. Now I'll bring in the new variable here, so that is v is equal to tau minus u. So then this is equal to, now integral of say 0 to infinity, that is h of u into integral of minus infinity to plus infinity. Now this can be written as Rx of v into e power minus j omega. Now tau can be written as v plus u into dv into du. Now the tau term will become to v. So now when we expand this exponential term, so we'll get the integral of 0 to infinity, that is h of u into integral of minus infinity to plus infinity. So I'll before writing this, we'll split this term. So then we'll get 3 exponential terms, that is exponential of minus j omega u. So I'll write it here. So into minus infinity to plus infinity, an integral. This is Rx of v. I'll keep this term here. Sorry, we'll get 2 terms. So e power minus j omega v into dv. So now if you look into this, so this is nothing but our spectral density equation. So this can be written as h of j omega, or h of omega. So h of j omega into, it is a product of Sx of, it is Sx of j omega. So now it means that Sx, so it means it is Sxy of j omega. So it means the cross spectral density for the linear system will result in terms of frequency domain, it is the multiplication of the transfer function with the spectral density of the input, that is x. So that is what it will result in. Now let us look into the autocorrelation of this linear system. Let me save this page here. Let's quickly look into this autocorrelation process. of this linear system. So we know the Ry of tau is equal to an expectation of y of t into y of t plus tau. Now from the linear system, we know the output will result in the convolution. Therefore we can write this as y of t is equal to an integral of 0 to infinity, that is h of u into x of t minus u into du. Then when we substitute this autocorrelation function in this case, we will get this as, so this is equal to an integral of 0 to infinity, this is h of v into integral of 0 to infinity. It means for each of these terms we are substituting here in this case. So that is nothing but, let me write here. So when we apply the expectation for each of this case, it is again the convolution function. So then we will get this here as the integral of 0 to infinity, that is h of v into x of t minus v into dv into integral of 0 to infinity, that is h of u into x of t plus tau minus u into du. So it means we are substituting for each of these terms in this correlation function. Now this is your y of t and this is your y of t plus tau. So from this definition we know what is our y of t here, so that we have substituted. Now we have to apply the expectation for this. So let us apply the expectation. So then let us rearrange these terms. So 0 to infinity, your h term, the impulse response is a constant. Let us take it outside. So h of v integral, and here, so this is left hand side is ry of tau. So right hand side is rearranging this impulse response, h of v and h of u into, so when we combine these terms, that is into expectation of x of t minus v into x of t plus tau minus, this is t plus tau minus u into dv into du. So this is nothing but our autocorrelation function. So this autocorrelation of x, so this is nothing but 0 to infinity. So this is h of v into integral of 0 to infinity h of u into, this is rx of tau plus v minus u into du into dv. So this is what we'll get. Then in terms of its spectral density, if you want to relate this, then we'll go for the next page here. So then from the spectral density we know the equation, that is Sx of w is equal to integral of minus infinity to plus infinity. It is Rx of tau into a e power minus j omega tau into d tau. The same thing we are going to apply for this case. Now it is Sy of omega equals integral of minus infinity plus infinity. Now we are going to substitute Ry of tau into e power minus j omega tau into d tau. Now we know the what is the autocorrelation of y in the previous case, so we are going to substitute. So this integral will be there, that is minus and plus infinity, and that is from the previous definition, it is 0 to infinity h of v into integral 0 to infinity h of u into Rx of tau plus V minus U into e power minus j omega tau into d tau into du into dv. So now we'll rearrange this equation as integral of, I'll take this integral of minus and plus infinity inside. So then this will result in h of v into integral of, then we'll bring in one more new term and then only we'll rearrange this. So that is nothing but I'll bring in w. So w is equal to tau plus v minus u. So then we have three exponential terms here. Just stop chatting here. So let us concentrate here. So then this will become, we have three exponential term. Then we have this from 0 to infinity h of v into exponential of j omega v. So here the tau will be replaced with w minus v plus u. So then we have these terms here. So this is into dv, and this is from integral of 0 to infinity. Then h of u into e power minus j omega u into du, and then integral of minus infinity to plus infinity, we have this Rx of w into e power minus j omega w into dw. And finally, if you can look this equation looks like the h of minus j omega. Why? Because here exponential term is plus, so it is, that is why we'll get minus here, into, and this is also one more the transfer function, that is h of j omega into, this is nothing but our spectral density in terms of x, so this is written as sx of j omega. So this is what the finally we will get for the autocorrelation function for the transfer function. So this is for sy of j omega. So in terms of the magnitude, if you write, so this is nothing but it is magnitude of h of j omega whole square into sx of j omega. So this is what finally we will get for the autocorrelation of the linear system, autocorrelation function of a linear system. Okay then, thank you for watching this tutorial.